Okay, so our next speaker is Aleksander Kubica, who's calling in from Poland. So just whilst he's getting set up, so his talk is about decoders, and in particular, an efficient color code decoder in more than 2 dimensions. Thank you, Aleksander.
Hello, everyone. Today I'll be talking about color code decoding, and this is a joint work with Nicolas Delfos at Microsoft. So let's get started. Our community wants to build a quantum computer. However, it's a difficult task. And I want to think about a process of arriving at a fault-tolerant universal quantum computer as a multi-stage process. First, we need to identify physical systems which we're gonna base our architecture on. So for instance, superconducting qubits. And then we would like to abstract from the details of the physical system and just think about a bunch of qubits affected by some noise. And then using some smart techniques from quantum error correction, we can suppress the noise affecting physical qubits and arrive at good quality logical qubits. And if our logical qubits are sufficiently good, we can forget all along about the fact that the quantum computer is built of noisy components and just think of an ideal quantum computer and think about running quantum algorithms on it. So in this talk, I will focus on the middle stage and on quantum error correction. And in particular, when we think of quantum error correcting codes, we want certain properties from those codes. So first and foremost, they better be implementable in the lab. We also want that there are efficient decoders with high thresholds for those codes. And if we're interested not only in quantum memory, but also in computation, we want to have easy fault-tolerant logical gates implemented on the encoded information. And the color code satisfies those 3 requirements. So in the talk, I will focus on stabilizer codes. So a code space is a subspace of the Hilbert space, which is the +1 eigenspace of all the stabilizers. And so the quantum error correction game we want to play is as follows. We have logical information, which we encode in the code, but then there is some noise, which moves us outside of the code space. And in order to revert that, we will measure certain stabilizers. The measurement outcomes are called syndrome. And this will allow us to find a recovery operator, which brings us back to the code space. And if the logical information after the whole process is the same as the initial logical information, we succeeded in protecting quantum information. The middle step of this process, I would refer to it as decoding. In other words, a decoding is the classical algorithm to find error correction from the observed syndrome. And lastly, the notion which is essential for the talk is the notion of a threshold. Roughly speaking, a threshold is the maximal error rate which can be tolerated by a decoder and the code. And of course, the threshold depends on the noise model we assume. Last thing I would like to motivate is why I care about the color code. We've all heard at some point that one of the leading approaches to scalable quantum computing is the 2D toric code. However, there are some difficulties there. Namely, it is quite resource intensive to implement a fault-tolerant non-Clifford gate in the toric code. And such a gate is necessary if we want to have a universal computation, if we want to implement universal computation. So here's where the color code comes into play. I'd like to think about the color code as an alternative to the toric code. And so first, color code is more qubit efficient. And also the color code has interesting transversal gates. In particular, in the dimensions, we have z rotations by the angle pi over 2 to the d. And also the color code provides a way of avoiding magic state distillation. And here I would like to mention the recently proposed idea of colorful quantum computing by Hector Bombin. Unfortunately, there seem to be some issues with the color code, and namely, the color code seems more challenging to decode, and it also seems to perform worse than the toric code. However, those issues are not a real problem, as we'll see. Which brings me to the main result of the talk. In the talk, I will describe two efficient decoders with high thresholds for the color code in 2 or more dimensions. So for simplicity, we'll start with talking about the toric and color codes in 2 dimensions. Then we'll see with an example what the restriction decoder is. And you should think of this decoder as a simple color code decoding strategy, which can use any toric code decoder. And then I'll show to you some numerical simulations of a threshold, and we will see that the color code threshold is on a par with the 2D toric code threshold. And lastly, I'll make a brief comment about the realistic scenario in which we think of boundaries, the circuit level noise model, and some hardware limitations. So let's get started. In the talk, I will focus on a special class of codes, the CSS stabilizer codes. And with those codes, we can correct X and Z errors separately. And so for the rest of the talk, I'll just assume that we have Z errors in the system. So what's the 2D toric code? It can be defined on the square grid by placing qubits on the edges of the grid. And the code is stabilized by 2 types of stabilized generators, the X-type vertex operator and Z-type plaquette operator. Okay, so now we have some Z-errors in the system. We can think of them as one-dimensional string-like objects. And the violated X-type stabilizers will correspond to endpoints of those strings as depicted in the figure. I will refer to violated X-type stabilizers as point-like excitations. There's a global Z2 symmetry in the system, namely, excitations in the toric code can be created in pairs because there will be even number of endpoints of Z-type string errors. So what is decoding in this case? And decoding can be viewed as nothing else but pairing up excitations. And we say that decoding is successful if and only if error and our correction differ by some stabilizer. Pictorially, what it means is that the initial error and our correction form loops which are contractible. So in the figure, I depicted a case in which decoding succeeded. However, the error and our correction can form non-contractible loops, and then decoding fails in that case. And the problem of the toric code has been studied quite extensively, and there are many toric code decoders. This list is by no means an exhaustive list. I just wanted to tell you that there are good and reliable methods of correcting the toric code. So now let's switch gears and let's talk about the 2D color code. First, we need to describe the lattice. We require that the lattice is composed of triangles, and the vertices of the lattice are 3-colorable. And then we can define the 2D color code by placing qubits on the triangles of the lattice and identifying stabilizers with the vertices of the lattice. Namely, for each vertex, we will have an X-type stabilizer and a Z-type stabilizer supported on all neighboring qubits. And despite the fact that the color code and the toric codes are related, it seems that the decoding of the color code is more challenging. And why is that? Let's see that in an example. So if we have a weight 2 ZZ error in the system, this will lead, as illustrated here, to 2 green excitations. However, if we have a single Z error in the system, it will create a triple of excitations, red, green, and blue. So now we see that the excitations in the color code can not only be created in pairs, but also in triples. So if we want to decode the color code, we need to account for those processes in which we create 3 excitations at the same time. And there is a global Z2 cross Z2 symmetry in the system, and this symmetry shows up in the following: the total number of red and green excitations in the system is even, so is the total number of red and blue excitations in the system. This observation will be crucial for the restriction decoder. So let me remind you what the setup is. So in the system, there are some errors which are identified with subsets of triangular faces. This is some two-dimensional object. But what we know is the syndrome. The syndrome is a zero-dimensional object. It's the locations of point-like excitations. So before we proceed, let me tell you what the restricted lattice and the restricted syndrome are. So we define the restricted red-green lattice to be the lattice obtained from the initial one by keeping only red and green vertices and edges between them. And the restricted syndrome RG is the original syndrome restricted to the lattice, to the restricted lattice. Okay, so the idea of the restriction decoder is quite simple. We start with a zero-dimensional syndrome, and then using some toric codecoder, we will get some one-dimensional object, which we later use to find out an estimate of the error in the system. And we get from 1D to 2D with some local lifting procedure. So let's see with an example how the decoder, restriction decoder works. So in the first step, we use toric codecoder for the red-green restricted lattice. Within this restricted lattice, we pair up the excitations. I denote the pairing by thick blue edges. I will do the same thing with the restricted red-blue lattice. And the pairing in that red-blue lattice, I will depict with thick green edges. Now, I will combine those two pairings. And that's what I have at this step of the algorithm. And notice that I don't know where errors happen. So I don't know the locations of shaded triangles. In the second step of the algorithm, what I will do is the following. For any red vertex in the lattice, I will find neighboring faces whose boundary locally matches the pairings from step 1. So let's see that with an example. For this red vertex, I find some subset of neighboring faces, hatched pink faces whose boundary matches the pairing. And I do it for each and every red vertex in the lattice. And in the last step, I will return as a color code correction all the faces picked in step 1. And this is a valid color code correction. So now let me make a couple of comments on the restriction decoder. First of all, any toric code decoder can be used as a subroutine in the restriction decoder. Also in our work, we prove a theorem which states that the restriction decoder succeeds if and only if toric code decoding succeeds. And from that, we can infer that the color code threshold, when we use the restriction decoder, is determined by the toric code threshold. Also, I would like to contrast the restriction decoder with previously proposed decoding by projection. First, the restriction decoder never aborts, and it uses only 2 restricted lattices. Also, and this is important, the restriction decoder uses a local lifting procedure, which allows us to generalize this decoder to higher dimensions quite straightforwardly. So I'd like to think of the restriction decoder as an efficient solution to the color code decoding problem in the dimensions. So when you have the d-dimensional color code, the problem of decoding of that code can be reduced to the problem of decoding the d-dimensional toric code. And then depending on the dimensionality of the toric code excitations, for instance, if they are point-like excitations, then we can use, for instance, the minimum weight perfect matching decoder. And if we have higher dimensional excitations in the toric code, then we can use, for instance, some cellular automata decoders, such as the sweep decoder. Now I'd like to show you some numerics. So what we looked at is the two-dimensional color code on a lattice dual to the 488 lattice. And the lattice is on a torus, and we look at the phase flip noise model and ideal measurements. And what we see is that the color code threshold is around 10.2%, and this is on a par with the toric code threshold with the minimum weight perfect matching algorithm. In the restriction decoder, here we use as a subroutine the minimum weight perfect matching decoder. Our numbers should be contrasted with other simple and efficient high threshold decoders. So we see a clear improvement. And also, if we want an almost linear time decoder for the color code, we can use, instead of the minimum weight perfect matching, we can use the union find as a subroutine to decode the color code. We did that, and what we observed is that the performance is pretty much unaffected. Also, I would like to make a comment about a realistic scenario in which we want to consider a system on the lattice with boundaries, for instance, the triangular color code. And we want to think of a procedure of extracting syndrome, which is done via some quantum circuit with ancilla qubits and noisy components. And we may also want to impose some hardware limitations, such as qubits have to be placed on a 2D plane, and we can implement CNOTs only between nearest neighbors. So it turns out that the restriction decoder can be adapted to the circuit level noise model, and we can also satisfy those hardware imposed limitations. If you want to learn more about that, I would advertise Chris Chamberlain's talk later today. What I would like to contrast the restriction decoder with is the following. It can be adapted to the circuit level noise model because it's quite simple. And this is not so easy for the other high threshold decoders, such as tensor network decoders or neural network decoders. And with that, I would like to summarize my talk. And I'll show to you a plug and play color code decoding strategy, the restriction decoder, which works in any dimension. And this strategy relies on the toric code decoding and some local listing procedure. We saw that the restriction decoder gives a high threshold, and this is better than efficient decoders for 2D color code and on a par with 2D toric code decoders. This decoding strategy can be adapted to boundaries and circuit level noise model. And as the take home from my talk, I would want to say that quantum computing based on color code is definitely worth pursuing. With that, thank you for your attention.
Thank you very much, Aleksander. Really nice talk. So perhaps I could ask a question whilst the question's coming. I forgot to mention the Slack channel, so it's session 6, talk 2, Kubica. So whilst the questions come in, and then I'll just ask a quick question myself. So my understanding of the toric code is that you get a nice decoder because one error creates two syndrome, means two syndromes light up, and so you have a graph problem to solve. Whereas naively in the color code, one error creates causes three syndromes to light up, and so you have a hypergraph problem. And so if you just try to tackle that in the same way as you would the toric code, you quickly get unstuck because hypergraph matching is hard. And so you're so by cancelling out one of, so you showed the example in the 2D color code where you remove one of the colors, and so you get back to a graph problem again. Could you explain a bit more about the D-dimensional case? I mean, just remind us what a three-dimensional toric code does that have? How many syndromes light up when you have a single error, for example?
So in higher dimensions, depending on your errors, either X or Z errors, they can create excitations of different dimensionality. And so, for instance, I think I have a slide on that. So, for instance, here, in a three-dimensional color code, you will have zero-dimensional point-like excitations and one-dimensional loop-like excitations. And similarly, in the toric code, you would also have point-like excitations and loop-like excitations. So for point-like excitations in the dimensions, you would have d+1 different colors of excitations. And for higher dimensional objects, you will have quite a few different colors of your excitations, and you would need to be able to match them correctly. But the general idea is very similar to the one I depicted to you in 2 dimensions, which is you consider only some subsets of your excitations, and within those subsets of excitations, you can do the matching. For point-like excitations, you can do it with minimum weight perfect matching. For higher dimensional excitations, what you would be doing is you would be finding a k-dimensional object whose boundary matches the observed syndrome. So in 3 dimensions, the problem boils down to finding some filling of loop-like objects. But yeah, in higher dimensions, you can, for instance, be thinking of filling some collection of spheres.
Thank you. So a question from Janitor May. So she asks, I see that you are assuming ideal syndrome extraction, right? So how would you account for the realistic measurement error? So you touched on that a little bit towards the end. Could you elaborate a bit more?
Yes. So in my talk, I didn't quite explain that, and that was a topic of some other work with Christian Berlan, Ted Yoder, and Guanyu Zhu. In that work, we looked at this realistic scenario of the triangular color code. That model has boundaries. We specified the syndrome. We specified the circuits to extract stabilizer measurements, and we laid out our data qubits and ancilla qubits on a 2-dimensional plane in a way that qubits, neighboring qubits, where we want to apply C-nodes, the qubits where we want to apply C-nodes are neighbors. And in that case, we assumed that the noise model is described by the circuit level noise model. We did some simulations, and we observed thresholds of the order of 0.2% for the triangular color code and the restriction decoder in the case of the circuit level noise model. And this is quite similar to the thresholds of the toric code, where we also assume circuit level noise model and some hardware limitations.
Thank you. So Barbara Terhal asks, is the restriction decoder effectively equivalent to the minimum energy decoding in the statistical mechanics model?
I don't think so.
Okay, thank you. Linglang Lao asks, could you say something more about the runtime of the decoder?
Yeah, that's a nice question. So the decoder, the runtime of the decoder, let's see. We would need to use the toric code decoder in 2 dimensions twice. So this is the bottleneck of the runtime of the decoder, because the second step of the restriction decoder, which is the local lifting procedure, and this can be done for each and every red vertex of the lattice in parallel. And it requires only, the complexity of finding the subset of faces, the neighboring faces, is constant. So it's determined by the number of faces around the vertex, but that number is constant. So the bottleneck of the restriction decoder is the complexity of the toric code decoder. So in particular, if we use the minimum weight perfect matching decoder, then it can scale polynomially in the number of lattice constituents. But if we, for instance, use the union find decoder, and its complexity scales almost linearly in the lattice size. So that's how we can get a color code decoder based on the union find, which has almost linear time complexity.
Thank you. So final question then from Joanne Champs, who asks, so the toric code is analogous to electromagnetism, with stabilizers being the constraints, so Gauss law for the electric field and zero curl for magnetic field. Is the color code related to QCD with 3 colors for quarks?
Well, the color code is just 2 copies of the toric code. So you can really think of creating electric and magnetic excitations there. The only extra, but we would have like 2 types of electric excitations and 2 types of magnetic excitations. So it should be viewed on the same footing as the toric code.
Okay, thank you again, Aleksander, for a great talk.
Thank you.
So more questions on the Slack channel after the talk. And so we're going to finish now for lunch. Session 7 starts at 10 to 3 UK time. Thank you very much. Bye.